because I have a big, suspicion that one of these days I'll forget.
Okay, sir.
Today I just remember at the last moment that I had to record. Okay, so please just even if it's redundant, okay, at least a chat something. Okay, have I started recording? Because this is very difficult to remember. No, it doesn't come intuitively that you record everything you say. Anyway, so today at least I've started. So let me share the screen. So can you see the whiteboard? Everybody can see the whiteboard? Huh?
Yes, sir.
Okay, let's start. Yeah, so basically we are looking at the the Fresnel formulae for EM waves at the interface of two dielectric media, right? Wow, I hope this handwriting continues. Anyway, so uh, R parallel, T parallel. So these are for p polarized light, and we also have the expressions for s polarized light. So R parallel is what? This is the what thing that I asked you to derive. क्या आता है? Tell me somebody.
Uh,
अरे, हाँ.
tan of I theta I minus theta t upon tan of
Yes,
theta I plus theta t.
very nice. Tan of theta I plus theta t. And in the same vein, this one you check. I hope what I'm writing is correct. 2 sine theta t. Guys, please check this expression. Okay, please check this. This is a bit complicated. Theta I plus theta. Did anybody try this out, by the way? Huh? This one?
Yes, sir.
ठीक है? मिला? ठीक है? Did it work
Yes, sir.
out?
Fine. Yes, sir.
Great, fantastic. I'm happy. Acha, and R perpendicular is sine theta I minus theta t by sine of theta I plus theta t, and t perpendicular is
The minus signs.
ये माइनस है क्या? हाँ, correct. See, I know I'll make a mistake. Correct. And t perpendicular is 2 sine theta t. अच्छा, ये वाला देखो. Is this correct? नीचे वाला तो same. Check this out. This one is correct. Somebody tried this.
Yes, yes.
Great. Acha, now the critical part, that is, we are going to look at the phase relationship between, basically between your incident and reflected waves. So, which is essentially looking at the sign of this R and T, R parallel and perpendicular, but for, so this is basically for different polarizations and obviously for different Ri, right? For different Ri. In the sense that okay, I should not say different RI relationships, I should say, right? That is better to write, because what I'm talking about is how Ni and Nt are different from each other. That is what we are interested in at the moment. Fantastic. Okay. Okay, so let us try to plot. Okay. So from here, what is the very clear takeaway for R perpendicular? So R perpendicular is very clear, right? I mean, whatever you have, so that is S polarized. So R perpendicular, what does it tell you? That for Ni greater than Nt, what do we have? क्या है तेरा so Ni greater than अच्छा Ni greater than Nt. So then your sine theta t is more than theta I, right? ठीक है ना? So R perpendicular is what? Positive or negative? क्या? अरे? What? Tell me, guys. Don't keep silent. Like, it's very. Anyway, I can't see your eyes. And now it looks like I'm
Positive.
talking alone. In a strange feeling, it's I'm alone in a room and talking away. It's feelings like, feels like I'm crazy or something. Please respond. So this is what positive, right? Because
Yes.
theta t is obviously then theta t is more than theta I. So this is the numerator is then always positive, because sine theta minus theta is negative, right? So sine R perpendicular is in phase with incident wave. And the interesting part, of course, is not interesting. It's like whatever Ni less than Nt, then R perpendicular is always pi out of phase. Is this clear? Correct? Because that is always negative, and there is no interesting phenomena. So if I had to draw a graph, I would basically draw कि अगर so like if I just do a graph of so this is my, so say for RT, so this is for Ni greater than Nt, and this is my say phase, relative phase, okay, and this is angle, or let's say theta I. So this is always, say I'm saying that this is 0, that is pi, this is always always 0. And what will be the other one? Ni less than Nt, again phi versus pi theta I, this is always pi. Fine, right? No problems at all. Okay, so maybe I will go to the other new thing differently. So for the other one, that is much more interesting, right? So let us just write down that formula again. That is for R parallel. So R parallel matlab you have tan theta I minus theta t by tan theta I plus theta t. So very interesting. This is a nice expression. This is a complex expression, and you can straight see that the moment I have, this implies I have theta I plus theta t equals pi by 2. What happens? What happens? Our parallel just
Zero.
away, right? So basically, it is 0. So the phase phi becomes 0. So basically, yeah, it's always in phase. I mean, the parallel itself. Well, that's not a correct thing to say. What you should say is our parallel is 0, right? So that it just becomes. I mean, it does not exist. So that is called what? This is called the Rooster angle, right? Right? So what does that mean? So when I have this kind of thing where I have this as in reflected and this as incident, then essentially this is 90 degrees, right? Yeah, so this one is then my theta b. By the way, can you, so essentially what does that say? That at 90 degrees, I do not have any reflected component. So can you argue this physically? I know that people who had done the fiber experiment, I know I discussed, but can you argue physically why should this happen? Anyone? You understand the question, right? I'm saying that from this mathematics, you can see that if I have this theta I plus theta t to be 90 degrees, which is the same as this, that is very clear, right? That this is theta I, this is the same, this is 90 minus theta I, and obviously this will be this is theta t, 90 minus theta t. If you add those two together, you'll have theta I plus theta t to be 90. This angle will be 90 essentially, right? So now, can anybody physically argue, guys?
Sir, it may be that because it's perpendicular, it can't have any component on the refractive index on the other side of the interface.
Pianuj, what does that mean? That is you're
I
stating
know.
what is happening, yeah. It is what is perpendicular. Mane kya answer hua? You're just stating the thing again. Why should there be, if this is 90 degrees, why should there be no reflected component? That is my question.
Sir, may I try?
Why are you asking? Of course, everybody
Okay,
can
sir.
try. See, we need
Okay,
to
sir.
make this interactive. So as many people want, please keep on trying. Bolo.
So because the reflected ray becomes plane polarized, and in this case, it will have no component because we are assuming this parallel thing, that is S wave. So
Hey, wait. S wave now. This is P. So I'm coming with P polarized light. And I'm
it
claiming
means,
that
sir,
when this angle is 90 degrees, there is no reflected component. Everything is transmitted. What does that mean?
so you are
What does
using
that mean? Why
R
should that
parallel.
happen? Huh?
So you are
These
using
are
R
parallel.
parallel.
Obviously. Hey, guys, come on, boss. I had explained this in detail. Rohan, forgot completely. Huh? Very bad. No idea, anybody. Can you at least guess? You understand the question? This should intrigue you, right? I mean, you're at this level where you should start questioning every damn thing. I mean, see, this is a mathematical thing, right? Why the hell should it happen? What is the physics? I mean, come on. I mean, this is something quite remarkable, right? You're having light coming and then the damn thing doesn't reflect. Where the hell? Why the hell? Why should it happen like that? You should have the curiosity, right? And you should not be satisfied with just an equation. You have to ask yourself, why does this happen?
So because cos 90 is 0. Naive guess.
Again, you're giving a math answer. I don't want math. Yeah, math is the language of physics, but physics is the thing happening. So why is there? So this is miraculous, right? You're coming with the right. Nothing is happening. Everything is going through. It's crazy, right? Why?
So actually, at the point of reflection, there the
Ah,
at the point of reflection, the
ah,
k vector and the polarization vector direction will be the same.
very good.
That's why.
ये कोई
That's why.
समझा? Who is this? Who is this?
Actually, my name is Soumo.
Somo. You're Sesi, na?
No, sir. I am RS
Oh,
99.
RS. This year you joined. This year you joined.
Yes, sir.
Ah.
Yes, sir.
Well, Shombo is absolutely given the correct answer, but did anybody understand this? Well, Chombo, you're not completely correct. You are kind of correct, but you're not completely correct. So what Chombo says is the direction of K and the polarization vector is the same, which is
At the point of
close
reflection.
to being correct, but not completely correct. There is a very yeah. So what Chombo is saying that electric field is in the direction of K, which actually well yeah that is well, Shomon needs to get a slight bit deeper, slightly deeper. What you have said is actually correct. I mean, if there has to be a reflected ray, then the direction of the electric field will become the same as the K vector. That is exactly what is correct. But why is that? Shomo, can you tell me that? Why will that be the case? That's absolutely right.
Because for the transverse electromagnetic wave, a direction of E and K vector should not be
Ah, that is
having.
correct. No, but I'm saying, why do you think that the direction of electric field will be the same as the K vector? In this case. Whereas, see, okay, let me
Because
just draw this figure again. Let me just draw this figure again. Arey, why the hell does it become slanted here? So this is what I am
for the
getting, right?
because for the transmitted ray, actually,
Uh,
a transmitted ray that is 90 degrees the reflected ray.
yes, so
So
let us draw this a bit nicely. So this is my electric field. Taito? This is my
yes,
electric
sir.
field, right? So that is the direction of electric field. So essentially here, that is like the electric field direction.
Hmm.
So
So
what
at the point of
Shombo is
reflection,
saying, exactly. So at this point, this is the electric field and that is the K vector as well. So what Shombo
that
is
is
saying,
not
that is
possible.
not, that is actually correct. Very good. So because the direction of E here and the direction of KR become the, so basically what he's saying is ER and KR are in the same direction.
If that reflected ray contains
Impossible.
that is not that is why that reflected ray does not contain that
Correct. So
vibration.
basically now if I go even a bit deeper, what is happening is, see, the electric field happens essentially because electrons oscillate. Okay, that is why you get this. So if I really go deep, why does a medium conduct any electric field? We'll learn that. So you know that essentially everything is a damp driven oscillator, right? The electrons, this I think the class understands that electrons are like, these are dielectrics, right? So the electrons are like bound, they are bound to atoms. So like they have some vibration frequency, but when the electric field comes, it actually comes as an externally driven driving force, and the electrons are basically depending on their polarizability or the susceptibility of the medium, they will start oscillating, right? And the oscillation essentially will happen, the electrons basically radiate perpendicular to the direction of oscillation. Now what is happening in this case is that if your electric field direction, and if I consider that the electrons are basically also oscillating in this thing, what is happening is if the electric field were to exist here, the direction of the oscillation of the electrons essentially become the same as the direction of the transmitted field, which is not possible at the interface. Basically at the interface, the direction of the electrons oscillating and the electric field become the same, which is not possible. Therefore you cannot have this, you will have only this. Is that clear? So basically what I'm saying is, electrons in dielectric, you have bound electrons oscillate due to external driving field, which is basically the electric field, dipole radiation, which is perpendicular to electron oscillation, which implies that for reflected wave at the interface, vibration of electrons is in the same direction of transmitted field, which is basically impossible. Does that make sense, guys?
Sir, can you explain the scenario where we don't have Brewster's angle? What will be the direction of electric field then? Like, how? What
That
difference
is
does it
always,
make?
see, as long, so see, basically, Rohan, as long as you, so see, essentially what is happening is you have the electric field always perpendicular to the k vector. And once this kind of a problem does not happen, that the k vector of one direction is the same as the field in the other direction, then this issue is not there at all. Because normally what happens is that you have the electric field, perpendicular here, they don't talk to each other. I mean, this direction is not that direction. Remember, these are, so the problem is happening at the interface.
Sir,
At
but why?
interface, suddenly you will have one direction electric field as same as the k vector in the other direction at that interface.
Why is that happening?
Once it
Why?
goes in the medium, then there's no issue. Okay, once they, so as long as that is not the case at the interface, you will always have a reflected and a transmitted. Okay, because they don't disturb each other, right? So as if you just have, oh, sorry.
I think, sir, Rohan asking why that is for the particular angle. Means
Yeah, that's what I'm saying. So if that is for a general angle, so just for a general angle, say, oh, say that this is my direction and that is my direction, right? And these two do not bother each other, right? Because this direction is not that direction. And this direction of the field here is not the k vector here. So think of the interface where you're actually
I got it.
say that the electric field at the interface is the same as the field that is propagating, right? So that cannot take off. The electric field at this side cannot take off. You think of the interface as a launching pad. You understand?
Yes,
Right?
sir.
So if you have the electric field direction as the k direction, this will not take off. It will just go through. Is that clear? So I don't
Yes.
think you understand. Yeah, you guys need to see this with. So let me just write something because these notes need to be probably self-explanatory. For other, sorry, for angles other than theta b, the issue of kt and er being in the same direction does not arise. Clear? Great, very nice. So I like this discussion. I hope you guys are appreciating and nobody is sleeping badly. Anyway, so now comes the interesting part. That is, we'll try to draw the phase for. So again, this is gone. So I'll need to write down the phase again so that we have that right in front of us. So you have R parallel is given by tan theta I minus theta t by tan theta I plus theta t. Let us draw it for, yeah. So for Ni less than Nt, I think the graph is pretty simple. Ni less than Nt mane, what is the thing? Then your theta I is greater than theta t. Okay,
Cost.
right? So that is positive. This is anyway positive. What happens right at the pi by 2 thing? Matlab 0 ho ja raha hai. So essentially what you have is, if I draw this as my 0 and draw this as my pi, kya ho raha hai? Ye 0 hai. Then at theta b, what happens at after theta b? Guys, what happens after theta b?
It jumps to pi.
Jumps to pi, right? Because then this, so all sine, tan, cos, na? So the second quadrant, tan is negative, right? So then our parallel becomes negative, right? So just what happens is this, oh god, this will jump. Jump by pi and just continue like that. No problems. The really interesting part comes when Ni is greater than Nt. Then you have all kinds of issues, right? Not all kinds. So initially, what's happening? Initially,
Negative.
very clear to all. Negative. Why negative?
Theta is less than theta.
Very clear, right? So then basically Ni greater than Nt mane then theta is lesser than theta t. Numerator is negative. So this is the whole thing is negative. At Brewster angle, Patak says 0. After Brewster angle, both become, this is negative, that is also negative, right? Then becomes
Yes.
0. Then suddenly something happens. What?
Totally internal reflection, I think.
Exactly. And that is something which is going to be your next assignment. I'm going to tell you how it looks like. The nature is like this. And that I cannot really predict from here. Okay. And this is what you guys have to find out yourselves by writing a Python or MATLAB code. Looking at, so basically this will have a real part and imaginary part. The phase will be the imaginary part, and you need to find that out and plot it with respect to changing theta I, which is like, so for theta I greater than theta c, this trend you guys need to find out. It's going to approach pi, asymptotically approach pi. Okay? And that is something I'm going to give you as an assignment. Okay, so that is the next assignment, and that's going to be due next week. So Thursday, and I will probably make this slightly going to be longer. By the way, so are all of you conversant with either Python or MATLAB? Guys, anybody not conversant with Python or MATLAB here? Just give me a chat. If it's not, if anybody is not conversant with Python or MATLAB. Anyway, if you're not conversant, I'm sorry, but you have to learn it. Because you're doing physics, it is imperative that you know one programming language. I would typically prefer, these days Python is hot, though I myself don't know any Python, but it is open source. I will always prefer something which is open source. However, if you are fine with MATLAB, that also is okay. But you need to do this, and I'll keep the assignment date as next Thursday. There's another problem besides this. Okay, so now let us look at the interesting case of the critical angle, which is, we now consider theta c, the critical angle. What is the meaning of this? So for that, we will basically again invoke, so that again that is happening only and only when I have arises only when theta I is greater than theta t, right? And why does that arise? So just if you look at it, so basically we can write, oh, by the way, one thing that I forgot to write, that is very clearly, you know that for Brewster angle, what is how is the refractive index related to Brewster angle? Please keep this in mind. Anybody? Rooster angle is equal to what?
And NT by NI.
So this is a very interesting thing. Suppose you were asked to measure the refractive index of a dielectric slab which is in air. Of course, because one assumes that you know one of these angles, then this is a very nice a way of finding out this. So we can actually discuss. In fact, in the assignment, I'll put this also as a question. How do you feel one can measure the refractive index of a dielectric slab? I will ask you to draw an experimental apparatus for measuring this. Okay, because you need to think at least how you can measure things, because even if you do not indulge in experiments or whatever you want to be a theoretician or something, unless you have an idea about experiments, you can never ever succeed in physics. Please keep that in mind. Okay, anyway, so right, so basically this starts from the Snell's law thing, that is, you know that sine theta t is nt by ni by nt sine theta I, right? Fine, right? Sine theta I by sine theta t is yeah, sine theta t by sine theta I is ni by nt. So basically Snell's law is basically nt sine theta t is ni sine theta I. This is Snell's law, right? So then what is from here, what can I write? So cos theta t is very clearly 1 minus ni by nt whole square sine square theta I the power of half, right? Which is nothing but nt square minus ni square sine square theta I half by this is nt square. Acha. By the way, so sine, what is another relationship that I can write for the critical angle? How does the Snell's law change? What is the critical angle, by the way? At critical angle, what happens? At theta I equal to theta c, what happens? Huh? Oi, what is theta t? What happens to the transmitted angle?
90 degrees.
Right? So basically sine theta c is nothing but nt by ni. Fine? Which means I can write this chap as ni square sine square theta c minus ni square sine square theta c by ni square sine square. Acha, this is actually what one can, sorry, acha, I am keeping this general. This is not theta c, this is theta I. Right? Because I am looking at all angles. This is theta I. Sine square, this is essentially nothing but, yeah, this is the same, sine square theta c. This bracket is full. Sorry, yaar. Right, so then I get this as nothing but sine square theta c minus sine square theta I half by sine theta c. What happens when, and this is equal to cos theta t. And at theta I greater than theta c, what happens to cos theta t? Huh? What happens? Cos theta t?
Complex.
Imaginary. Right? Which means I can write this as plus minus I sine square theta I minus sine square theta c by sine theta c power half. Right? So basically this means that at beyond my critical angle, the cos theta t is imaginary. So that has tremendous consequences, right? Fantastic consequences. Can somebody tell me the consequences? What this actually signifies? How do we find out the consequence? Essentially,
There is something wrong in the previous slide.
what is wrong?
That you wrote that that theta c happens theta I greater than no.
Where did it go? Oh, this one, right? What? Vishwajit, come again? Huh? What is wrong?
That we can consider that theta c, the critical angle, arises only when theta I greater than theta t.
Yes, theta I is greater than theta c, right? At critical angle is different. I'm saying at theta I more than that, right? More than critical angle.
No,
obviously.
No, you wrote theta I greater than theta t.
थीटा t कहाँ लिखा? थीटा c है ना?
No, not here. Not here, sir. After that.
Oh, okay. Sorry, very sorry. Thank you.
That will be theta
that time you should have said. Anyway, thank you. See, I will keep on making these silly mistakes. Okay, please warn me immediately. That does not make any sense, right? That doesn't make any sense, right? And we basically so basically we this is actually not correct. So what we are saying that I think this does not make sense. The statement doesn't make sense.
Less than
theta t, what we should write is theta t greater than pi by 2.
Theta is less than this.
Right. So we should basically write when the transmitted angle is greater than 90 degrees. Still, this is not correct. Arises only when I wanted to basically write when Ni greater than Nt. This is what I wanted to write. Okay, this is what I wanted to write. I somehow wrote theta I and all that. Okay, so basically arises only when Ni is greater than Nt. Thank you. This is consistent. Okay, why is this? I hope it does not go and hang, right? Okay, yeah. So, what are the consequences of this? I'm sure some of you know this, the consequences of this imaginary component. Yeah, you know?
Total internal reflection.
That's so obvious, but more deeper.
Okay. Reflectance become unity.
Consequences of evanescent wave. Correct. Of theta I greater than theta c. Right? So how do we do it? Let us consider the electric field as some E0t e to the I kt dot r minus omega t. Okay. So basically what I'm meaning is, so I have my incident angle here, like that, and of course this is bending more, right? Because this is ulta. So this is my theta I, that is my theta t, and obviously you have, this is your theta r equals theta I. This is ni, that is nt. This is what I'm talking about, okay? And I'm saying that this is my z and that is my x. Okay, this is my wait, wrong.
Theta t.
yeah, ये back करूंगा तो सब चला जाएगा. Let me just. Oh, shucks. Damn. This, that. This is nt, that is ni, z, that is x. Fine. Okay. So basically what I'm saying is your xz is the plane of incidence, right? And obviously you have, say, if I say something like kt r hat, that is something like ktx x plus ktz z. And I can write this as some kt sine theta t x hat plus kt cos theta t z hat. Is that fine? Fine, right? Now you know that cos theta t, now cos theta t is nothing but sine square theta c minus, actually let me write down the whatever, sine square theta c minus sine square theta I by sine square theta c half, and for theta I greater than theta c, you have cos theta t equals plus minus I sine square theta I minus sine square theta c half by sine theta c. Okay, fine. So now let us just consider, if I just let me take this and put this guy here. Okay, so basically I'm trying to find out physically what is happening. Okay, so basically what I will have is your ET is now some E0t e to the I kt ni by nt sine theta I x hat plus minus, acha, the time part we don't care about, okay? Sine square theta I minus sine square theta c half by sine theta c z hat, right? And you have obviously okay, the time part I'm not considering omega t. Okay, so then obviously what you're having is basically Et is e to the I kt ni by nt sine theta I x hat, and now comes the physics. So what is this telling you guys? So basically, in the z, what do you have? What do you have in the z? You actually have, so there is a plus minus, right? So you will have either, if you take this minus sign, what do you have? You have an exponential growing function. If you have the plus I, you have an exponentially decaying function, which is physically possible.
Decaying.
You cannot have the negative sign because that essentially means a diverging function, which is going to violate conservation of energy. So that is not physically possible. So the math gives you two possibilities. Physics rules out one. So what you are going to get is a decaying exponential in the z direction. E to the minus, I forgot the k as usual, kt minus kt sine square theta I minus sine square theta c half y sine theta c z hat. So basically this means, what are the properties of this? What does this tell you in the sense of the physical properties of this, of the decaying part? Rhea? So if you just think of this, we can write this part as some e to the minus beta z, right? Obviously, this is very clearly unphysical.
Why the ink is become faded, sir?
Sorry, what? Vishwajit, what?
This ink is too faded, I think. Take a deep ink.
Ink is too faded. How can I do that? Make it bigger. Black ही तो choose किया.
Sir, you can increase the size.
No, that is because you'll become okay. So that I can do. Oh, that तो इसके लिए again I have to go there and write. अरे भाई. बाप रे बाप. This is problematic. Oh, you. Sorry. Yeah. Anyway, so essentially you have something like this, right? So what you can directly see is that this beta of same, no? Choose this. No change here. I can't. This is slightly deeper, no? So this beta is like the attenuation constant, right? So this is like a k, and roughly you can say that beta is of the order of lambda because it's like a k, right? So essentially you have an exponentially decaying wave in z. And what do you have? Is there any propagating wave anywhere, guys? Is there any propagating wave
In x direction.
in the x direction, right? In the x you have an evanescent, well actually evanescent wave, this is not correct. Evanescent wave is this decaying thing. So basically you have an, what is the meaning of evanescent? Huh? You know what is the meaning of evanescent? What, guys?
Oscillating but does not propagate.
Chat. That is, come on, Rohan. There is a world outside physics. What is the meaning of
Uh,
evanescent as an English word?
it means quick or something happens in a flash.
Basically means something that is vanishing. You know, there's an English word called ephemeral, something that is essentially which is there but not there, something like that. Which is like it's like extremely, it's not like short span. It's not there's not it's not like there's not a very quantitative adjective or quantitative adjective. Something which is, it's like a flight of my, I mean, in classical English, I'm saying, not in the physics part. In fact, physics has borrowed this from English. Okay. Physics has borrowed this from English, and evanescent is something which is basically, it is there but not there types, like a dreamy quality. And this wave essentially is vanishingly, I mean, the extent of the wave is vanishingly small. Why am I saying that? Why am I saying that it's vanishingly small? Huh?
Because beta is the order of lambda, so
Correct.
it can just
Because it's
propagate.
decaying so fast. Because it's decaying so fast.
No, I mean to
However,
say it can penetrate only up to some certain wavelengths into that.
correct. In the X, you have a traveling wave. Okay, so what are the other qualities? Very crucial. This is okay. So, acha. Now let me pose to you the conundrum. It is basically saying what we have something where at critical angle evanescent wave exists even though theta t is imaginary. Okay. Now let me pose this. Why the hell should it be there? Let me just ask you very strongly. Because you're clearly seeing that when there is something called total internal reflection, right? This is essentially called total internal reflection. Everything gets reflected. So why on earth do we have something that is getting outside? We have clearly seen that theta t cannot be more than 90, right? It doesn't make sense. So the entire wave has to come back. So why the hell do you have something that is peeping out? Why? What is the physics? Now again, physics. Why is there any requirement for this evanescent wave to exist? Physically, what is happening?
Energy conservation.
Huh? What?
Sir, to conserve the energy total.
Energy. What energy? Why energy? Energy conservation kahan hai, Rohan? You are coming with energy. You think there is any propagating energy going outside? No way. Acha. No way. Okay, since Rohan has brought it up, let us just solve. So energy is represented by what? Energy is represented by what, guys?
Square of the amplitude of the
No, propagating energy is
Pointing
given by pointing vector. Propagating energy is the pointing vector. Let us calculate that. What is that? That is the real part of 1 by mu E cross B, right? And in the Z direction, it will be what? Right? Right? Is that fine? So why is this? I don't know. Pen ka ink cannot go right. I mean, why does this thing become so narrow? It's crazy, I don't understand. Is there something called recharging this pen or something? Why is it getting so thin anyway? I hope there are no secrets in this pen. Anyway, so let us find this out. This you agree with, right? This is a Z component of the E cross B is what we are interested in. So basically this E cross B means what? 1 by mu E cross KT cross E. Is that fine? Is that fine? 1 by mu KT KT E dot E minus E dot KT E. Fine. Cross A cross B cross C, right? B A dot C minus A dot C B. Correct? What is E dot KT? E dot KT is? अरे क्या हुआ?
0.
So we have left with real part of, this is all real part of KT E square dot Z. Fine. Now comes the maza. So what is this KT dot Z mane? What? KT dot Z, how can I write this as? KT dot Z is what? KT dot Z mane? K dot Z matlab KT cos theta T, right? Is that correct? What? KT dot Z is cos theta T, right? K dot Z.
Yes.
And what is the real part of cos theta T?
That is purely imaginary.
What is the real part
0.
of cos theta T?
0.
Sz is 0. Where is your conservation of energy gone, Rohan? This is clearly telling you no propagating energy in evanescent wave.
Sir, can it be conservation of momentum?
तुम एक के बाद एक बोल रहे हो. Conservation of momentum कैसे आ गया? Explain yourself.
I'm just
Explain
guessing.
yourself. And random think मत करो गुरु. No, but good. You're thinking nice. ऐसा ही आएगा answer. There is something more fundamental. Don't go into this part. There is something more fundamental. I hope my pen. Anyway, yeah. Socho. What is the most crucial? This entire Fresnel theory is based on one huge assumption or requirement. What is that? If I ask you to describe me the one thing on which this Fresnel theory is based, what is that? All these equations we wrote, it was based on what?
Boundary conditions.
Let me go to a new slide.
The
Let me go to a new
amplitudes have
slide.
to be like a EI.
We
EI should be
neglected
equal to
absorption.
ET plus.
No. Just think. Let me write it down.
So the phase at the interacting surface.
What is the most अभी फिट ठीक हो गया fundamental assumption of the, let me hear from you guys. Vishwajit, you know the answer, don't say.
I think somebody just said that.
What?
Said the
Yeah.
answer actually.
Absorption. We neglect the absorption.
Oh, no absorption. Yeah, that is not. Yeah, that we are saying that, but that, why do you call it fundamental? Yeah, you're saying that. No, but again. See, there is a mistake. You guys are first getting the answer and then you are justifying it. Of course, you are basically saying that because 1 minus TR gives you 1 minus TP gives you RP or something, right? RP plus TP is 1. That you are saying. I am not saying that. Even before you start deriving, what is the basic thing on which everything is based on? There was something we assumed. There was
Sir,
something we assumed. Bolo?
at the interacting surface, the phase difference is not there, right? The
No,
base.
where is phase coming, guys? What is, we wrote those conditions, right? We wrote some stuff. All these derivations came because we wrote all those electric field, magnetic field things. What were those?
So is it the boundary conditions?
Yes. What is the boundary condition?
Yeah, the
So the tangential component remains.
Yes.
Like someone already said.
Tangential component of E cannot vanish, and therefore you require a Z component of E. Is this argument good? You cannot have that disappear. There has to be a Z component of Z of E. But how are we complying with the math? How are we complying with the math? Because on the other hand, you have a strange, the theta t is imaginary. It cannot be more than 90. So where is the sort of adjustment coming? How are we? See, physics is all about explaining physical phenomena without compromising the maths. So where do you think we are not compromising with the math? Because the math tells us that theta t is greater than pi by 2, you cannot have anything going out. But you need to have, for this whole entire, this premise to hold, you need a tangential component of the field to get through. But at the same time, you're saying that there cannot be any propagating field. There is my hint, propagating field. There is no propagating field. There is no propagating field as well. You have an electric field, there is only intensity, no energy flow. You understand? This is a beautiful example of physics working, keeping the math perfectly consistent. This is, I consider this as one of the greatest examples of how we get, how physics is different from math. That you actually have, you take, you only use the physics is the language, math is the language of physics. We cannot absolutely compromise, but it is different because for different physical phenomena, we take out possibilities of math. We cannot, there are some stuff which leads to physical phenomena which cannot happen. There are some stuff which, which are crucial, some assumptions which we have taken, which we have to have consistent. We cannot compromise those. Here we could not compromise with the fact that we need a tangential component of E to remain. Therefore, we have the z component of field. At the same time, we cannot have a propagating component because the angle of the transmitted angle is more than pi by 2. So we say, and it beautifully comes that there is only a traveling wave on the surface. The only flow of energy is on the surface, and this is essentially something, you know what this leads to, what this phenomena where you have a small decay of the field, vanishingly small distance, but decaying into the second medium. That is one aspect. The other is there is this surface wave which flows. Do you know what that leads to? This surface wave is
Plasmons.
exactly the phenomena of surface plasmon resonance. What are surface plasmons? Somebody has to give a talk on this. By the way, your talk topics, I will probably, we are still too early. Once we finish optics of metals, I think I'll upload those. By the way, if any of you are already targeting on things which you want to study or talk on, absolutely free to send me. Keep sending me the stuff if you particularly want to talk on something. Okay. So surface plasmon resonance is a fantastic phenomena, pretty new phenomena, and that takes advantage of the fact that you have these bound electrons on the surface which actually behave like one big electron sea, and this one sort of traveling X wave that is able to excite all of them simultaneously, right? And you have this massive surface plasmon resonance. There is a plasmon wavelength that is you're going to study when we do the metal thing. This happens essentially at dielectric, but in a sense that you can excite plasmons when you have the absorptance wavelength in some kind of feasible region, right? Doesn't make sense if that is completely far off or not achievable. When you have a dielectric metal interface, these wavelengths at which, so you have a lambda, I mean lambda one and not distance, you have a wavelength of the electromagnetic wave, right? That wavelength has to be usable, some visible, IR, microwave, whatever. So when you have a metal and a dielectric, you have this happening very beautifully. Okay, and why is so? Let me ask you another question. That is, do you think this this propagating this evanescent wave? Do you think it is useful? Is it of any what is it's? But you have this electric field which is dying out so quickly. So is it just an artifact, a completely useless artifact? What do you think? Is it a useless artifact which has no, usability at all? So understand what is happening. The
Isn't
field is
this
dying out at like lambda.
sorry, what's the
My
question?
question is, you have the electric field in the Z dying out within a region of lambda, which is extremely small, right? So it is almost vanishing. It's almost not there. So do you think there is any utility associated with it? Is there some interesting feature that you perceive? The evanescent field. Interesting characteristic. Anything interesting you find here, guys? Think what is happening. What is the so typically what is a lambda? Tell me what is a, if I ask you, tell me a value of lambda. What is that comes into your head first? Just unthinkingly tell me. Unthinkingly, quickly. What is the value of lambda you think of? All right,
600
great answer.
nanometer.
Lambda is 600 nanometer. you have a field dying out at 600. Is it useless completely? Is it utterly useless?
Sir, very close to that interface, the field is still significant. So if we have some very thin film or something like that, then
Again, shall I just interrupt you? So what I want to get from you is, what is something inherent in the field itself which is quite marvelous? Inherent. The fact that it is dying out so quickly. What makes it still interesting? What makes it unique? What makes it have something which is impossible to get in any other situation?
So it's skin depth.
Skin depth is there, but what is that? Is that a definition, right? Skin depth is a definition. It is like a skin depth. It's not skin depth. It is like skin depth. Skin depth is in a metal. You have the electric field decaying. That is different reason, no? It's because metal.
Yeah, I mean,
Yeah,
with
it's
a beta
another
factor,
word of
with the
describing.
beta factor.
Okay, so electric field, what are the aspects of the electric field that you? What are the properties of the field? Let me get this from you. What are the properties of an electric field? What are the things that you have?
It oscillates.
Oscillation. No, how do you characterize a field? Okay, let me ask you this. How do you characterize
amplitude and phase.
amplitude? उससे क्या आता है? There is, in experiment you get amplitude.
No, we
No,
get
intensity.
Intensity. What is the definition of intensity?
Squared
अरे
amplitude.
और amplitude square बोल थोड़ा experimentalist से बोलो यार. It's an experiment. You get amplitude. Experiment में how do you measure intensity? If you have a light beam, how do you measure intensity?
You have a small time frame in which you collect all the photons coming.
You guys, this is not the photonic pictures, Priyanuj, please. This is real. If I give you a laser beam, you'll count photons to find out intensity.
Measuring current.
How will you measure intensity from that, my friend? You guys don't think it was like, bolo. I give you a, this is a basic question. I give you a laser beam, I give you a photodiode, and I give you a scale. How will you find out intensity? How will you find out intensity, whole class? If you are not sleeping, please answer this. I give you a laser beam, you have a laser, switch it on, I give you a power meter, I give you a scale. Can you measure intensity? And nothing else. You're not given a photon counter, nothing. Not giving a watch also.
By measuring diode current. So.
That is photodiode, yeah. Photodiode gives you intensity. What does photodiode give you?
Current, sir. Photocurrent.
Photodiode gives you a laser. What? Oh, you guys, okay. Guys who did the optics lab, yeah, at least you know, huh? When you were doing the fiber experiment, the photodiode was giving you what of the laser?
Power.
Power, yes.
Power.
So how do you get intensity from there?
Intensity by
area is power.
Yeah.
Intensity by area is power.
No.
Oh my goodness, yeah, you'll give me a heart attack. Please don't forget this.
Power by area.
Power by area. ये class 10 में सीखा था शायद. And you guys, just because you have learned photons, the only way you understand intensity is number of photons. And so many times I've told you that is not the experimentalist way of understanding what intensity is of a light beam. We'll never get that. So now do you understand what this means? That the entire field is decaying in 600 nanometers. Do you realize the humongous intensity that this field has? You can actually beat something called the diffraction limit in these evanescent waves. That is not so. Essentially, if you focus a beam through a laser, so how do you increase intensity? How do you increase intensity most effectively?
Sir, what are you putting it as area?
Area of the beam.
The beam width.
Beam width, yes.
Okay.
Area of the beam, means cross section of the beam. Right? Lower the beam radius or beam dia. You understand? So evanescent fields basically have huge intensity, and essentially you break something called the diffraction limit. I will not tell you what that is. People who are interested, please read it up. Anybody has any idea what is the diffraction limit? Any idea? What is the meaning of diffraction limit? Anybody any idea?
So it's related to like the resolution of imaging and stuff.
No, it's much not as yeah, that is correct. But basically, so when we learn this in the course, when you focus a beam or well, yeah, so laser beam or something through a lens, then the minimum spot size that you obtain is given by the diffraction limit. So for any propagating beam, you cannot go to lower spot sizes than this thing called diffraction limit, that can only and only be broken by using evanescent fields. You can generate humongous intensity which cannot be obtained otherwise, and that has a lot of use in optical trapping itself, because you can generate enormous laser intensities and therefore very high stiffness optical traps. Okay, so again, people who are interested, you can read further about this. I will just end by noting this can generate very powerful optical traps. Okay, I end here. I have an assignment which I will again post. Assignment deadline will be, this is the assignment. We will sort of post this on the drive, and I'll actually put one more thing on this, that is how you describe an apparatus by which you can measure the Brewster angle. I mean, sorry, the refractive index of a glass slab. That is something which I'm going to also ask you. Okay, so yeah, I basically wanted to finish this thing. Therefore, we have had a very long class, so I hope people are not utterly bored, but I thought I at least enjoyed the discussion. So if you have any questions, please come now, or else you can always ask me on WhatsApp or anything. You know that I'm always available for questions. Any questions, by the way, guys? It's been pretty long. Yeah.
Yeah,
okay.
sir. Just could you explain again how the intensity would be very high? Like just
Because
like
the
in a
spot size, if you think of, Priyanuj, the spot size, if you think of, the area of the extent of the beam is sub-wavelength. Okay, the extent of the beam is of the order of the wavelength of light. So wavelength of light, matlab, it is extraordinarily small. So that the intensity, when it's like the area that you take, it's divided by that extent, the square of that, that's going to be huge.
Okay.
Right? Because the denominator is absolutely fantastically large. It's like E by, I is always E by R square, no? Pi R square or whatever. Is this clear to everybody? It's very simple. E by pi R square. R is extraordinarily small. You cannot get smaller R's by focusing using a lens. The other way that you reduce beam size is by focusing, right? But by focusing, you can never get to such sub-wavelength regions. You're always constrained to lambda, and probably more than that. Sub-wavelength you only get by this. Okay.
Sir, so would the intensity be higher than the intensity of the beam, like just before the interface? That's like
obviously
a question.
because the beam will, so certainly,
It will
right?
be higher than that also.
Of course, I mean, intensity is not a conserved. It's like not a conserved quantity, right?
Energy
Intensity is not
not
conserved. Doesn't make sense. It's just a way of understanding the beam. It's not a conserved quantity, right? Momentum, etc., are different. Okay, I thought, so this is a very interesting topic. This has launched a whole field in physics. The thing of surface plasmon resonance. There are local plasmons, there are surface plasmons, all kinds of very interesting things. But the root of that is essentially the tangential component of the field having to be continuous. Okay. Okay. So we end now. Meet on next Monday. Bye.